Continuing on with our discussion on quantum mechanics, we have the Schrodinger equation. In the previous video, we took a look at matter waves and how very small particles like electrons and atoms can behave like a wave, can have wave properties as long as they have energy and momentum. The equation describing the energy and momentum of a wave function is known as the Schrodinger equation. The time-dependent Schrodinger equation is given by the following equation. Negative h bar over 2m, double partial differentiation of psi with respect to x, plus u times psi is equal to I h bar, partial differentiation of psi with respect to time, f, and we have f is equal to negative partial differentiation of u with respect to time. U is the potential energy of the particle, whereas F is the force that is applied on the particle. In analyzing wave functions or in determining the wave function of a particular particle, we use the Schrodinger equation. Let us now consider the special case of the free particle. A free particle is a particle that experiences no force. F is equal to 0. Since f is just differentiation of u with respect to x, if f is 0, that means u is not changing with respect to x. That means u is constant. If u is constant, the potential energy of the particle does not change. For simplicity, let us consider u to be 0. If we let u be equal to 0, u times psi will be equal to 0. We get the following equation. Negative h bar over 2m, double partial differentiation of psi with respect to x is equal to I h bar partial differentiation of psi with respect to time. One valid. Now, if we let u is constant with respect to time, to x rather, if the potential energy is likewise constant with respect to time, if the potential energy does not depend on time, one valid solution to this equation is given by psi of xt is equal to small psi of x e to the negative I omega t, where small psi is some time independent function, and e to the negative I omega t is referred to as the time modulation factor. One thing you will notice with regards to small psi, if we go back to this equation, to the previous equation, on the left side, we are differentiating psi with respect to x 2 times, whereas on this side, we are differentiating psi with respect to time. If you differentiate psi with respect to time, since small psi is just dependent on x, it will be outside the differentiation. You are just differentiating the time modulation factor. So the right side will result in psi of x still being present. That means on the left side, after double differentiating psi with respect to x. So since psi is comprised of psi, small psi, and the time modulation, and it's only small psi that is dependent on x, that means double differentiating psi will mean double differentiating small psi. So double differentiating small psi, and there is psi on the right side. That means on the left side, after double differentiating, psi must also still be present. This points to the cyclical characteristic of small psi, like say the cosine function or the sine function. So that's one characteristic of small psi that you need to take note of. Using this equation of psi, psi is equal to small psi e to the negative I omega t. Using this equation of psi into our Schrodinger equation, we are able to derive what is called the time-independent Schrodinger equation. Negative h bar over 2m double partial differentiation of psi plus u, a small psi rather, plus u small psi is equal to e small psi, where e is equal to h bar omega. H bar omega, E is the total energy of the matter wave. The time-independent Schrodinger equation. So if the energy and momentum does not depend on time, we can use the time-independent Schrodinger equation. The time-independent wave function small psi, the solutions to the wave function small psi must satisfy three conditions. The function small psi must be a continuous function, particularly throughout the region that we are analyzing. If you're just analyzing a limited region, in that region, psi must be a continuous function. Outside the region, small psi does not matter, as long as you are limiting your analysis in that region. In that region, small psi must be a continuous function. The first derivative of psi with respect to space, that is with respect to x, so differentiation of psi with respect to x, must also be continuous unless the potential V of that region is infinite. And small psi must not diverge when x goes to infinity, either positive infinity or negative infinity. So that's it for now. In the next video, we'll take a look at one application of Schrodinger's equation, the particle in a box situation. So thank you for watching.